was among the first group of graduate students I had at MIT when I moved there in the early 80s. There was Karl, Ron Rapp, and Eng-Sun Chan, I think, were the first of the group. And Karl took over some nonlinear wave work that I'd started with John Miles and another student while I was here, and really developed, really displayed a facility with the theory and numerical methods and doing laboratory work, and he's continued that, developing those skills, and I think it's probably fair to say that among the people working on nonlinear, long nonlinear internal waves in the ocean, that Karl is among a handful of people who can cover the theory and the numerical methods and also do laboratory experiments. And so he has, I think it's fair to say that a lot of observational physical oceanographers have rediscovered things that the theoreticians knew about these phenomena several decades before. And I think Karl probably plays a role of helping keep the community honest about what's going on. I hope I haven't weighed too much on you, Karl, but that's my perception. So I'd like to introduce Karl Helfrich.
I often hear myself saying, yes, you should go back and look at something. Anyway, before I get started, I just wanted to correct or add two comments that I think Ken was hard on himself yesterday when he was talking about his early teaching career. I was in that class, stratified flow class, and yes, there was, if I look back on it, there's probably evidence of kind of rushed preparation. But he was teaching from what was then quite recent, Owen Phillips' book on upper ocean physics and buoyancy effects in fluids. And so it was hard to go wrong. It's great topics. And I think I appreciate that when it was done, what I realized that it was just such a fascinating area that I said to myself, well, this is what I want to do. I want to do something like this. I found I was less interested in trying to find an answer than to understand what was going on. And I think that's the mark of a really good teacher, to excite somebody about a topic and make them enthusiastic about it. So I'm grateful for that. So anyway, let me see. Get this going. So when I thought about what I would talk about here, I thought, well, I can talk about some new stuff or some stuff that's recent, but that touches, I think, closely on some work that Ken and Gunnar did. I don't mean to bring back that Hermes Gunnar if it was not. But, so I'm going to give a couple stories, and I kind of titled it to have some punch of some strong effects of weak rotation on nonlinear internal waves. And this is work that I've done over the last 6 or 7 years, some of it in collaboration with Roger Grimshaw, who Ken knows well, and Ted Johnson. Both now, Ted has been at UCL, and Roger's changed his affiliation to there recently. And so these are just a couple pictures of one on the left, Sunglint, I believe, at Gibraltar, and you can see this surface signature of large amplitude internal waves radiating from the strait. So that's going to be part of the story. And the other one is an image from the South China Sea. That's that sort of landform in the middle is the Dongsha Plateau. And I can't see it very well, but you can see a couple of wavefronts, and they've been radiated, or they've developed out of the internal tide that's radiated from the Luzon Strait further to the east. And in both cases, one can wonder if rotation plays an important role, and it can, and it can surprising role. And so I want to start off with this work that Ken had done, because there's a dynamical connection with what I'll talk about later. And the question at the time was, do solitary internal Kelvin waves exist in a rotating channel? And so the picture on the left is a depiction of a solitary wave. So it's pressed up against the bottom wall would be the right wall in the northern hemisphere. And it's got a classic squared shape, and it's got an exponential decay on the scale of the deformation radius across the channel. And it's a Kelvin wave, so there's initially only a U velocity. But the question is, do they exist as a compact solution? And the answer, well, it was uncertain, but there were some laboratory experiments by Tony Maxworthy and Dominique Renoir that showed that the transverse cross-channel decay, and there was a transverse cross-channel decay in wave amplitude, so there was a kind of a structure that was a little bit like a linear Kelvin wave, but there was wavefront curvature. And so the picture on the right is a laboratory experiment from Renoir to measure the wave amplitude. But the most important thing was that the wave amplitude decays down the channel with the propagation distance. Okay, so it's not stationary. Could be dissipation. But another important clue was that Tony Maxworthy in particular noticed the radiation of inertia gravity waves behind this leading Kelvin wave. Okay, so it suggested some sort of coupling. And there was a numerical study by Katsas and Aquilas where they solved what's called the rotating economics of Affiliation equations. So it's in the KDV class of models. And they found results that were qualitatively similar to the laboratory experiments. Still wasn't clear what was going on. And so Roger and Ken wrote a nice theoretical paper looking at this RPP equation. And there were a number of things came out of it, but there were certain strong integral constraints associated with the equation that come out from the derivation. And they imply strongly that locally confined solutions are not possible due to this radiation, or what would seem to be radiation into the Poincare part of the spectrum. Anyway, this Gunnar will recognize this. I just wanted to show what this looks like. This is out of the paper here. Ken, Gunnar, and Dominique Renoir. Gunnar, I'm sure, made this calculations. So this is the initial Kelvin wave. It's got the squared shape and an exponential decay across the channel. And initially, no v velocity. L sub r is the deformation radius based on the long wave phase speed and the rotation rate. And so what you can see in these numerical calculations is you develop wavefront curvature across the channel, and behind the wave you radiate a lot of energy into the Poincare part of the spectrum. And so Ken, in this paper, and Gunnar and Dominique, a really simple explanation. It was more than that. I mean, they showed directly that there was, showed theoretically, that there was a direct resonance between the nonlinear Kelvin wave and the Poincare modes in the channel. So if you look at just the waves in a channel, you have the linear waves in a channel, you have a rotating channel, you have the Kelvin wave mode, you have the geostrophic non-propagating mode, and you have these Poincare wave modes that are quantized across the channel. And so if you draw this dispersion diagram, you have a Kelvin wave along here, and these are each of the Poincare modes. And so a solitary wave, solitary Kelvin wave, would have a phase speed or a dispersion relationship omega over k that was constant or linear in this diagram, but it was slightly, the slope slightly elevated from the linear wave. And so you can see that the Kelvin wave has the potential to directly resonate with the wave. So this is just potential, but the important part is that they showed, Ken and others showed that this actually happens. All right, it's quite efficient. So I want to discuss a couple problems where we're going to look at the interaction of solitary waves and these Poincare waves. And we're going to look at it from 2 points of view. Just like this thing, we're going to look at it where you imagine you're going to start with a solitary wave. And I'm going to consider that a short wave in the problem that I'm interested in. The Poincare modes are going to be long waves. And if you want to make them legal, they're the internal tide. All right? And the solitary waves are the short waves. So you've got two waves in the system, long and short. Okay, so we're going to start thinking about short wave. Okay? And although we don't have to, it's nice to think about a simple model. And the simple model I'm going to frame some of this on is what's called the Ostrowski equation. So this is like the rotating KP equation, except it's invariant in Y. There's no channel, so it's one-dimensional. And it's weakly nonlinear, weakly non-hydrostatic waves with rotation. So you have a little bit of nonlinearity, a little bit of non-hydrostatic dispersion and rotation, and they come in sympathy, so that what you get here is a KdV equation in here where alpha, beta, and gamma here are coefficients that depend on the environment, the waveguide itself. I'm not worried about them. And then you get this rotational part. And the interesting thing about this equation is that you have nonlinearity, which we often think is balanced by the non-hydrostatic dispersion. But in fact, this nonlinearity can be balanced by the rotational dispersion. And the rotational dispersion is different because you can see this is really an integral differential equation. So the rotational dispersion is not local. So it's a different thing. And there's this additional zero mass constraint, which is important. We'll dwell on it. So this equation is kind of interesting. It's really complex. It's more complex in many ways than the KdV equation. And much of what I'm going to say isn't restricted to this weakly nonlinear model. We see these things in more realistic models, but this is a good first order approximation. So if I set the non-hydrostatic dispersion and the rotation to 0, you end up with the Hopf equation, or just a simple wave equation, and that always gives you breaking in finite time. Okay? And if we get rid of the rotation but now include the dispersion, you get the KdV equation, and so we have these short in comparison, solitary waves. On the other hand, if the non-hydrostatic dispersion is 0, but we keep rotation, we get something called the reduced Ostrowski equation, where nonlinearity is balanced by the rotational dispersion. Can be. And this equation is quite interesting. So these are the long periodic inertia gravity waves, or tides. The interesting thing is this equation also permits breaking. Ken will know that, and Alexei. But in this context, John Boyd first showed this. Now these periodic inertia gravity waves are interesting. They branch from a sine-like wave all the way up to a wave of maximum amplitude that we're approaching here, that in fact is cusp-shaped. It's just a connection of parabolic arcs. And so that you move from 0 amplitude up to a limiting amplitude. So these periodic waves exist over a range of amplitudes. Okay. And if you're worried about including things like cubic nonlinearity and so on, this stuff still persists, although some of the forms change. So this full equation, you can show that the localized solitary waves don't exist for the quantity beta 1, gamma 1, the two coefficients here greater than 0, and that's the case for oceanic conditions. However, there are what are called special quasi-conoidal waves. These are periodic solutions, and what they are is essentially one of these inertia gravity waves with a solitary wave appended to it right on the crest. Okay, so they're funny form. You just balance the motion of the solitary wave with the propagation of the inertia gravity wave. So the solitary wave is riding on a background state that's not 0. It's on a current. But there's some interesting stuff that happens. So get this to go the right way. I think I've learned. So if we start with the short solitary waves as the initial condition, Roger showed that because of this radiation into Poincare spectrum, the solitary wave will decay to 0 in finite time. All right, and the time scale is here, and it's a couple rotational inertial periods. It's not fast, but it's not inconsequential. And so here's a numerical calculation. This, in fact, with a fully nonlinear wave model, but it doesn't really matter. Here's the initial solitary wave, so this is x in the moving frame, and this is time in this thing, so these are just slices, and this solitary wave, you can see it decays as it propagates forward. As it decays, it's radiating the Poincare waves behind it. Take a look at these Poincare waves. These things aren't linear. They are approaching that cusp-like form. All right? And you can understand this. This is just another version of the diagram that Ken and Gunnar and Dominika showed. but now I've written in terms of the phase speed for the linear dispersion relationship of the Ostrovsky equation. So this is the case where there's no rotation, so we branch from the linear long wave phase speed, and as the wave number gets larger, the curve dips down. On the other hand, if you include this rotational term, it should be k to minus 2, I'm sure it's right. The curve is this one here. And so you can see that the solitary wave, which would sit up around in here, if it could exist, would directly resonate with the Poincare waves. This is just another way of looking at what Kennedy shown. But the other thing, this is a clue, of course, that these solitary waves can't exist with rotation because there's no gap in the spectrum. There's no place for them to reside. They normally need to be separated from other linear modes. What's interesting, though, is what happens next. And if we take a look at that over a little bit longer time scale, here's the decay of this leading wave. And it's radiating Poincare waves. But the Poincare waves themselves steepen, and there's a kind of a recurrence. So we've radiated waves into the Poincare waves, but we've formed through steepening of the inertia gravity waves another localized solitary type wave. It radiates, and the process repeats itself. So there's kind of a recurrence that goes on. So you wait long enough, and what you get is a localized packet. And this is just a snapshot of the localized packet. You can see in this case it's highly nonlinear. There is something like a solitary wave, and there's something like an envelope that envelops this thing. And if I look at the energy in this particular nonlinear system, you can derive an energy, and if you just integrate it with time in the area of this packet, you look at it falls rapidly, and then it settles into something really steady. So it's a localized packet. And they're really kind of interesting. You can start with two of them, and they pass through one another, so it's suggesting solid envelope type of stuff. On the other hand, you can do other cases where, in fact, they merge. So it's a much more complicated system, at least in this. And the other thing is, if you start from the general initial condition, just a Gaussian bump, eventually you organize into these packets. So this is the kind of long-time outcome of the radiation into the Poincare spectrum, is that it reorganizes itself into some sort of nonlinear wave packet. So let's think about this. Really the easiest thing is to come back to this Ostrovsky equation, and it can be rescaled kind of into itself so that all the coefficients are 1. Okay. In that case, the only parameter in the thing is the amplitude of the initial solid KdV solitary wave. And so you can think of increasing, these are numerical calculations, of increasing amplitude in this way. And so that's fixed rotation, but increasing the wave amplitude. Or you can fix the amplitude and increase rotation. So the point of it is, though, no matter what you do, the outcome is a localized packet. In this case, looks more like linear waves, a little bit more nonlinearity. And then here's this very asymmetric packet that we saw before. But this is the natural outcome, long time, through this radiation process. So how do you want to think about it? If we go back to that linear dispersion diagram of the Ostrovsky equation, it turns out here's the phase speed in blue and the group speed, C sub G, in red. And so this gives a hint of what's going on here. There's a maximum in the group speed. So there's a kind of a natural sorting here from sort of the general system. You're going to sort naturally. You're going to find at long time a particular selected linear wave number, K sub C, critical wave number state, that you expect to see out front. And if you were to do a linear problem, this would be the leading disturbance would be an area wave type solution, right? But you saw those packets, they're symmetric. That's not an area wave solution, that's nonlinear involved. So how do we explain this? And of course, this is where Roger comes in. These packets are governed qualitatively by an extended nonlinear Schrodinger equation derived from the Ostrovsky equation. So you do the usual thing, you look for a slowly varying packet around a fast carrier wave, and you crank through the machinery, and what you end up with is, this is the nonlinear Schrodinger equation, and we've included some extra terms here. If you remember, the selected wave number is at the maximum of the group speed, so omega kk is 0 at that point, and so this term, the standard dispersion term in the Schrödinger equation, is gone, and you need to go to higher order to explain the packets. And so once you do that, you can find envelope solitary wave solutions. So that seems to explain what's going on. We're looking for these at that selected fastest group speed wave. And if you compare the numerical calculations, Ostrovsky equation, varying the amplitude at some long time, compared to the dash line, which is that envelope solution, you can see, well, for small amplitude, it's not bad. And of course, as the things get more nonlinearity, you start to pull away pretty quickly from the approximations of an approximate equation to get to the envelope. But nonetheless, it seems to show the underlying physics, how things are sorting, how you can establish a packet. And so one of the other things Ken said to me very early in my career is that I should try to go and do an experiment in Grenoble. And it took me a long time to do it, but we finally finagled it. This is where Ted Johnson comes in, because to go there and use this now, it helps to have EU colleagues and EU money, best of all. And so I didn't get to spend 6 months in Grenoble, but I did get to spend about a month in September several years ago there. And I have to say, it was fantastic. Compared to my lab, when I work, it's like I'm cooking for myself, right? It's not that much fun sometimes. But you go here, this is a good restaurant. I mean, they work for you, right? You say, this is what we want to do, and they do this wonderful stuff. And so we went to do these experiments in Grenoble. This is the big rotating table, which is a very simple lock-release experiment that followed some earlier work that Dominique Renoir did. But he didn't have this theory which to interpret it. He was interpreting it in a different way, looking for solitary waves of the Ostrovsky equation, compact solutions, not the envelopes. And we know they don't exist. So we just do these simple dam break experiments where we have a lock release, and we let a wavefront propagate down here. We record the wave amplitude. It's in a two-layered system. We record the wave amplitude with these sort of ultrasonic transducers that give us the interfacial displacement. We also use optical thickness methods to get a plan view of the wave amplitude as it propagates down, because there's going to be a little geometric spreading. I'm not going to talk about that. It turns out, though, that that's not crucial to what's going on at all. So we did these experiments, and I don't know if you recognize the Ken, master experimentalist up there. What's that? No.
Was this
Henri? No, that's not Henri. But yes, Henri was involved, and Joel Samaria, and Louis Gaston, who was there for a while. Him and Samuel Bibot was taken over for Henri. But Henri, this was one of the last experiments that Henri was involved in, because it was shortly after this, we tried to go back to do some other things where they broke the lab down and they had to make way for light rail. It's been moved across Grenoble. It took them about 3 or 4 years to redo it. It's on the other side near the university, right near Legion. And so we've been trying to go back, we just can't get back in. Anyway, that's Roger Grimshaw, master experimentalist, up in the control center. We let him go up there, but we didn't let him touch anything. Anyway, so this is one of those experiments. This is a non-rotating case. Here's a solitary wave. And this is down the tank, and these are scaled in a particular way. It's not important right here. You see there's a nice solitary wave with trailing radiation. That's what you'd expect. And if you look at the spectrum, this is from the optical thickness, you can see the solitary wave. It's a depression, so it's blue. And you look at the spectrum, this is K versus omega. Here's the linear dispersion relationship, and the solitary wave shows up as this constant line, just what you expect. If you do the same thing with rotation, here's this leading solitary wave shortly after the lock release. You can see there's a lot of other stuff here, but it's actually starting to organize differently. And if you wait a little longer, further down the tank, here you can see now very clearly a packet. All right. So there's development of a clear leading packet, and it turns out the carrier with a clear carrier wave frequency or wave number, a clear phase speed that's greater than the group speed. Okay. And so if we also look at this is the optical thickness down the tank. You can see the propagation of the fronts through the envelope here. So there's clear distinction group speed and phase speed. And if we look at the dispersion diagram, This is the linear dispersion diagram. You can see all the energy is concentrated down in here. And this point is, in fact, the maximum root speed. So according to theory, all the energy should be piled up right there. But of course, this dispersion diagram includes everything in here, so there's other stuff going on. But it's, you know, it's in the right ballpark. So just a quick summary of these experiments. If we have different lock heights, and if we move down this way, we're increasing rotation. So this is near the release point. This is further down the tank. So this is no rotation, solitary wave, trailing dispersion. And as you move to higher rotation, you see very early on organizing into a packet, and then leading packet down here. And it's more obvious over here for larger amplitudes. We develop these packets like this. So the important point here is that in the experiment, there's 4-aft symmetry of the packet. And that's an indication of the nonlinearity coming into play. If it were just purely linear sorting, you'd expect an airy wave type disturbance. There'd be some asymmetry. The other thing that's really quite important, I think, is that for increased rotation, so we're moving the leading solitary wave is eliminated, and the leading packet is an outcome of much more general initial conditions. So you can think of this as long-time evolution, not necessarily from solitary wave radiation, but any sort of disturbance like geostrophic adjustment. So you have geostrophic adjustment, you radiate the Poincare modes, and they can organize like this. And let me just move through just quickly then. And you can compare it to the weekly the envelope theory. This is amplitude, and this is a measure of the nonlinear correction to the speed of the envelope. And you can see that this dashed line is numerical solutions to the Ostrovsky equation on all the points or the experiments. And so that weakly nonlinear, or the extended NLS theory doesn't agree very well, but it doesn't agree very well in the wave number packet with the shape of the packet. But the Ostrovsky equation solutions and the experiments are okay. Okay, so that's part one. So there's a direct resonance with the inertia gravity waves that leads to decay of the initial solitary wave. And this is just a direct analogy with what we can. But the long time, the new thing here is that the long time outcome is a coherent nonlinear wave packet. And the carrier wave number corresponds to the maximum of the linear root speed for the Poincare part of the spectrum. And generally, the packet formation doesn't require an initial solitary wave. It's a more general outcome of something like this. And here's a couple of references. So I want to condition where the solitary waves and the rotational part of the spectrum interact in an interesting way. Let's turn this around. So part two. Let's take a look at the long wave initial condition. So we're going to turn it around and start with a long inertia gravity wave. And this you can think of as the internal tide. And it's the initial condition. And you might ask, how does it evolve and produce the short solitary wave? So this is a diagram that came out of consequence of a long ONR program to look at the wave radiation in the Luzon Strait. And what we discovered, people discovered, no surprise, is that you radiate a long internal tide. It takes, though, quite some time for this steepening of the tide to occur, and in fact, it doesn't always occur. It's frequency dependent, it's forcing dependent. So the question is why and how? So just to remind everybody, if we don't have any rotation, and you start with a sine wave, and here, don't worry about the numbers too much. What I'm doing it in such a scaled system, so that either I have rotation or not, and the sine of this, it's either 0 or 1, and the nonlinearity is scaled to 1, and then this beta is bringing in the weak non-hydrostatic effects. And it would be, this is a geophysical scaling. So you start with this internal tide, solid sine wave, and eventually we know it steepens and produces this packet. This is known for a long time. Breaking always occurs. That is, the steepening of the packet and the formation of the undular waves here, they're regularizing the shock. And the time to breaking for beta, much less than 1, is just given by the regular breaking, simple wave or Hopf equation breaking. The TISA breaking is proportional to 1 over the initial maximum initial negative, this is negative slope. Always goes to breaking. And in this case, the breaking point of the Hop equation is at 3 1/3, and so you can see right back here we're starting to do that process. Let's do everything the same. Let's just bring rotation back in. Same way, same everything, and you let it go. Boom, nothing happens. And in fact, if you continue this on forever, you're never going to go to breaking. And this has been known. Rotation inhibits the formation of internal solitary waves. Kevin Lamb showed that. Theo Birkema discussed that. And Theo especially noticed that it's supposed that it was due to the presence of these nonlinear inertial gravity wave solutions. And this is something that we also saw and tightened up. So, and this is all, but Lexi will recognize this is that a rotation in the case of a Kelvin wave, nonlinear, non-dispersive Kelvin wave, rotation delays the time of breaking, but in fact it always still goes to breaking. Is that right? It will always go to breaking. Let's just increase the amplitude of the initial condition. I think it was 0.3 before, now it's 0.5. In this case, amplitude's larger. You do go to breaking. You produce the short waves. They ride on the long wave. A whole lot of energy is left in the long wave. And this is geophysically important because, of course, this is a mechanism to get energy from large scales to small scales and ultimately maybe to dissipation. And well, definitely dissipation and maybe vertical mixing. Depends on how you do dissipation. So, is there a criterion that tells us when we make this transition? Could be maybe the initial amplitude. Maybe it's greater than the maximal nonlinear inertial gravity wave. So you just start with something that's bigger. And it's not so simple, right? Those waves aren't sine waves, so it's probably not simply an amplitude. The Ostrovsky equation is still pretty complicated and doesn't allow breaking or overturning because of this term. So what we're going to do is we're going to eliminate this term and ask, can we say something definite about breaking in the absence of non-hydrostatic dispersion? And this is the reduced Ostrovsky equation. Written here, I just got rid of this term. We can rescale it like this. So what do we know about this equation? Here's the paradox. This equation is known to be integrable. And for this equation, integrability says the solutions remain regular for all time. That's not true of all integral systems, but it is in this one. However, John Boyd showed numerically that breaking occurs for sinusoidal initial conditions in this equation, like this, whenever 3ak squared is greater than 1 plus or minus something. Very careful in that. These are contradictory results. Can we reconcile them? Can Boyd's criterion be proven and generalized for non-sinusoidal initial conditions? So just to tell you where Boyd's criterion comes from, let's take a look at it. Here's the derivation. Here's the equation. So what we want to do is just scale the nonlinear terms to the rotational term. And it's just u of x by u. If we say it's a sine wave, then it goes like ak squared. There's a hint that the area is bigger than the rotational dispersion. And so Boyd, in the original variables, Boyd's criterion, which we call the Ostrovsky number, on the left, it's just 3 alpha 1 gamma ak squared. Now here's a hint what's going on. AK squared is the curvature of the initial wave. So let's take a look at, this is just, these are numerical solutions of sine wave initial conditions scaled with wave number 1. It turns out there's a dilation theorem. You don't need to worry about trying different wavelengths. You can always restretch everything. So this is A of 0.3, so this Ostrovsky number is 0.9, and we integrate forward in time, we never see breaking. And these are done in a characteristic formulation, so it's very easy to see if there's breaking. You just look for the Jacobian of the map between the physical and characteristic variables to go to 0. Here's another example, slightly larger, OS is 1.2, and in fact it does go to breaking. This is just a confirmation of Boyd's criteria. These are sine waves. But here's something interesting. Here's two waves. They're very similar in shape. They're not sine waves. I'll tell you what they are later. There's 1 and there's 2. This is kind of equal to 0. They're pretty close, though. They're about the same amplitude. They don't look very much different. But if you wait a little while, one of them is just starting to break. It's tiny. It's a little micro breaker in this sense. But the other one isn't. So the distinction between these two is pretty subtle. It's not ample. Right? I've already told you what it is. So how do we find an exact criteria and resolve this apparent conundrum between the integrability of the equation and the observation that there's breaking? Well, proof of the integrability of this reduced Ostrovsky equation requires you, here's the trick, of course, that it requires you to transform from the original xt system into some characteristic coordinates, capital X and capital T. And you come, by doing this, you end up with another equation. Never heard of it before this, called the bullet-dot equation. It's known to be integrable. So the jump was, well, if that's integrable, that one is, right? But of course, however, for that transformation to be true, the Jacobian of the mapping must not vanish. And for this to be true, it can be shown from the Ostrovsky equation that this quantity f cubed, which is 1 minus 3 alpha 1 gamma eta xx, must be greater than 0. So there's the Ostrovsky number voids criteria. It's not enough, though, just to say that this has to be 0. In fact, you need to show, you can show that f is a conserved density, and this f obeys from the Ostrovsky equation, this equation, which in characteristic variables is just f phi. Phi is the Jacobian of the map. P d by dt, capital T, is 0, and that says that f phi is a conserved quantity. So once you label a point on the wave with this, it's conserved as it moves with it. And that's important. It can't change, because if you have a criterion about breaking, if that criterion, the Jacobian, changes in time, you're in trouble. Anyway, the outcome is that for any point where this f naught, the initial value, is equal to 0, whoops, for any point where f naught, something's off. Oh. Something seems off here. It just says that for every region between x1 and x2 of the initial wave, okay, here, so any point that's equal to 0 stays 0. So you can track the boundaries of any localized region between x1 and x2 where this f is less than 0. This will always produce a breaking front at x1. And the breaking condition is local and based on the curvature here. So it's a very definite criteria. So come back to this example that I showed you before. Here's a patch where this number is greater than 1. And if you follow, this is x1. If you follow it, it goes to breaking now. Once it goes to breaking, these red curvature indicators get haywire. And this is the Jacobian of the map. You can see as time goes, it drives down to 0 at some time that's greater than the prediction from the Mach equation. So this is the delay of breaking due to rotation. But it's definite breaking at the point where this analysis would predict. And now if you say, well, how is that when you add a little bit of dispersion in? Here's an example where we go to breaking. You see the breaking. In the case where there's no non-hydrostatic dispersion, now you add a little bit in. And in fact, you go to breaking and you produce the waves. And if you compare the two forms, the one that's broken here, because it's a characteristic method, we can go past the breaking and in here the wave. So you can see this is telling you something about what's going on. If I come back to this example where I had two waves, in fact, all I did is just combine a sine wave with this first harmonic and a little bit of phase shift. And each of these linear waves are independently stable according to the Voigt's criteria. However, the sum of them isn't necessarily, and these two are different by the maximum slope or maximum curvature. So one solid should go to breaking, the dashed one shouldn't, and in fact that's what we see. And just to emphasize this, you can have a really more general initial condition. This is just a Gaussian bump on a pedestal that satisfies the mass constraint. There are two patches here where the system should go to breaking, and in fact there are two breaking fronts in this particular example. So now let me finish up by thinking about how we might use this. So, Ken was nice. I work on theory, numerical stuff. I work in the lab. I haven't ever had the appetite for going to sea, which Ken does, but I've enjoyed working at Woods Hole with other people who do go to sea, because it's kind of restraint on me sometimes, but it's also a chance to influence the way people think about their observations. And so here's an example of trying to apply this theory. So this is from the South China Sea observations. David Farmer put these acoustic devices that measure travel time top to bottom. From the travel time display, times, you can, through a model that involves basically heaving of the first internal peritoneal mode, you can estimate the amplitude of the interfacial displacements as the wave goes by. So there, in these data, there are 3 of these pies measurements. There's one here, A1, A2, and A3. And so this is the record, a short period of record, just to be indicative of the wave that comes through here. This is an A1, so it's moving, and so the red is just an attempt to filter it. So this is the initial condition. And then further down here at A2 and A3, you see the filtered wave, which I'm trying to filter and show this is the remaining tide. Remember, some of the energy makes it into the fast part of the short wave part of the spectrum, if you want to call them short waves. In this context, they're solitary waves. So that's this stuff right here. You can't see it, I have to pull it out. One of the things that's very interesting about this is that the tides here are mixed. They're diurnal and semidiurnal, so they're 2 different frequencies. And in fact, that Ostrovsky criterion goes like 1 over f squared. Okay? And so the diurnal tide is much more stable to this because rotation, the frequency, omega over f, is such that, backwards here, the diurnal tide is much more stable because the frequencies are smaller, and so that drives the Ostrovsky number to a smaller value. So they tend to be stable. So in this mixed tide, it's the semidiurnal. In this situation, it's the semidiurnal tide that you're likely to see go to breaking, even though the amplitudes, pardon me, of the 2 tides might be different. And so here we are at this last measure. And you can see this part of the record, where the amplitudes are actually as large as some down here, don't produce the waves. And this has to do with the frequency content. When you get down here in the semidiurnal part of the tidal phase, you do produce a lot of these solitary waves. And so we can use that. We can take this record at A1, filter it, and compute the Ostrovsky number for the environmental conditions here. And there are a couple funny points here that are probably bad data that lead to high values of this right here, high curvature values, just because of biasing the data, and I didn't do very much to correct for that. But you can see that this number crawls up larger than 1, becomes larger than 1, principally down this part of the record. And then if we look at A2 and A3, I've then just removed what I've claimed to be the remaining internal tide and just show you the solitary waves. And so we really haven't done this. We really need to check this very carefully, but there's pretty clearly something connected there. There's another way that you can think about this. There are lots of places where you see very long-range propagation of the M2 internal tide. For example, north of Hawaii, right? Really, I mean, this 1,000 kilometers. Why shouldn't it maybe steeper? Why shouldn't something else happen? People, have all sorts of things. Parametric or subharmonic instability might occur, all sorts of other things. But one of the reasons you might expect this to be stable is that for these environmental parameters, the Ostrovsky number right here at the beginning is just marginal for kind of typical radiated tidal amplitudes. And as you go north, rotation increases. And as rotation increases, the Ostrovsky number goes like 1 over f squared. F is increasing. We just drive this to stability. So in fact, this thing is not going to steepen. So more likely with higher latitude to remain stable. And if you go to the equatorial regions, Sulu Sea, where the waves emerge really rapidly out of the radiated internal tide. So latitude, in fact, you expect that. And so there's probably something in this that tells you something about where what parts of the globe, and for what frequencies these inertia gravity waves stay. So anyway, just let me summarize here with, or I'll just leave that up there and take any questions.
So what happens with the Ostrowski equation if you replace the dispersive term with full linear dispersion? So you have like a Whittam type equation on the left-hand side. Do you get breaking in that?
I don't know. I suspect as long as it's small in some sense, you start with the long wave, it's bound to be small, I think. And I suspect you do it. I'm not sure. Certainly. It's true that, let me just back up, all of these things that I've shown are modified if you include, say you go to the Euler equations or Navier-Stokes or other forms. All this stuff follows through in qualitatively. The breaking criterion is exact only for this model equation. As soon as you add other things, things change. But it tells you something about how complicated it is. It's not some simple criteria based on amplitude. It's something different. And that was probably true even in the full system.
Again, the effect of weak rotation is really fascinating. Your theory is strictly one-dimensional, and in the first airview of the photograph, can there be some two-dimensional effect because the propagation distance, total propagation distance is very long. Therefore, would it be interesting to study the span-wise variation? Namely, you will have KP equation, full KP equation with partial Y. In that case,
You've done both.
you have done both.
So in the first part, if you add the geometric spreading, the KP part of it, you still get the packet organization. Quantitatively it's different,
That quantitative is
but you still get the packet organization. And there's a competition between how fast the sorting happens, the linear, essentially linear sorting, and the geometric spreading, the group speed propagation of energy lateral. But basically it happens.
and it's phenomena. Now, what is the in dimensional terms? What is the characteristic length of your solid ray wave or Gaussian?
So it depends on the situation.
Now, what is the roughly in that aerophotograph? Roughly, what is it? Kilometers.
8 kilometer, sort of 500 meters, kilometer, a couple kilometers is the scale of the
Very short.
solid with tide, depending on the situation, can range from 10s to 100 kilometers in the south times. The M2 tide is about 80 kilometers, I think, there, and the diurnal tide is longer. But even in the second part of breaking, if you add, if you go to the KP equation, and you add a little transverse initial structure, depending on how strong that is, you can dominate the transverse spreading of energy to dominate the approach to breaking. So that's another way to keep it stable. On the other hand, if it's not strong and that isn't fast, then you're going to go to breaking.
But so-called breaking is a good qualitative indication because it's always a weak and nonlinear equation are not cannot be extended all the way to breaking. The breaking is
Well, that's to identify that point. That's why we remove that non-hydrostatic dispersion. But you're right. That there's always something that's going to regularize the system.
Or not. It's nature.
Yeah. You're right.
Book.
Karl, question I have. The Ostrowski equation was derived for a two-layer system.
I just showed you that. You can have continuous stratification.
So there's extensions to continuous stratification.
Yeah.
Yes, it was. Okay, that's awesome.
I just showed it in case somebody wants to see.
Great. Well, I mean, my impression from this is things have moved a hell of a long way since what we were doing.
I'm glad because I sometimes think, part of my work is still some of the same stuff. And so I like to think
It's a lot.
I have to admit, I'm really grateful for Ken. I should have said that, I got started, he came with this problem that he had started with John Miles, and he talked about it in the class. And I said, that's neat. I want to learn about it, so I wrote a term paper. I found it a few years ago. I quickly put it down once I started reading it. This is, but it lit a fire, and it was a great time to start in this because Al Osborne had just made wonderful observations at the end. You can see it was shortly after Zabusky and Krustal found the solitary waves numerically. The inverse scattering transform had just been developed. So all this applied mathematics, physics, and observational oceanography was coming together. You know, I feel really lucky to have come along for Ken to have kind of seeded this, he and John Miles kind of seeded let me get started. So I've always appreciated the timing and the help.
Okay, enough of this mutual admiration.